I am Verena from Charles University in Prague, and I'm happy to talk today about expanding the tephrochronological records in the Alps and introduce the first discovery of the Lacher-See tephra in the Eastern Alps in Lake Plansee. I will talk about why we need tephrochronology and how it works, why distal tephra deposits are important. I will introduce you the Lacher-See eruption and its implications, followed by the distribution of the tephra, our discovery in the Eastern Alps, and why we may need to reassess the fallout map. Tephra studies apply to many disciplines. So besides their geological relevance, they allow us to build precise chronological frameworks and are used in bioenvironmental studies, archaeology, hazard assessment, and many more. What makes tephra unique is that it forms isochrones almost instantly after an eruption. This means the primary deposit has the same age everywhere it's found. So any age assigned to it can be transferred to all records that contain this tephra layer. With tephrochronology in the broad sense, we mean all aspects of tephra studies, whereby tephrostratigraphy includes the study of tephra layers and its deposits. And more narrowly, tephrochronology is the use of a tephra layer as an isochron to connect and synchronize sequences and transfer ages. So the main value of a tephra layer in terms of geochronology is their capacity to act as both a dated age marker as well as an event stratigraphic horizon, linking widespread sedimentary archives. The four main fields of application are improving chronological models, constraining climatic events, and assessing eruption histories and risks, and studying human-environment interactions. Cryptotephras refers to very fine ash, which we can't see with the naked eye, simply because they were transported for hundreds of kilometers where only very fine particles like glass shards and some crystals can remain. And this is crucial because it allows us to apply tephrochronology across much broader areas and ultimately enables the correlation between several geographic disparate records from marine to ice cores to terrestrial records. There are many environmental impacts related to ash dispersal, like major effects on climate and really whole ecosystems. And we see several of these impacts with the Lacher-See eruption. The Lacher-See volcano is situated in the Eifel volcanic field in Western Germany. Its most recent eruption was approximately 13,000 years ago and was the largest and most powerful eruption in Europe since the last glacial maximum, releasing about 150 megatons of sulfur. So it caused really major environmental disruption, like extensive damage of the ecosystem, impacts on human population, and major climatic effects linked to this massive release of sulfur. And understanding these effects emphasizes the region's volcanic potential, as this area is still volcanically active. However, to understand the full scope of an eruption, it's important that we understand how far the ash was distributed. And the eruption released approximately 20 cubic kilometers of tephra over an area of about 230,000 square kilometers. And the Lacher-See tephra is characterized by its distinct geochemical signature, and it's very precisely dated. So it's used as a precise tie point for various studies. And therefore, it is really a key marker for late glacial deposits in Europe, from deposits near the caldera to peat bogs and lakes hundreds of kilometers away. The Lacher-See tephra has been found at over more than 400 sites so far, from Sweden in the north to Poland in the east, to the French Jura in the west and Italy in the south. And the original 1985 fallout map depicts the LST fallout in a distinct three-lobed pattern based on findings which were available at that time. And this map still appears unchanged in many later studies. So most LST findings have been reported in regions which are covered by this three-lobed pattern, but there are major gaps, for instance, to the northwest and especially the east, including the Eastern Alps. Also, most findings come from organic-rich sediments, such as peat bogs and small lakes, where tephra layers are more easily identifiable. And this raises the question, does the pattern reflect actual fallout, or is it shaped by research bias and understudied areas like classic alpine lakes? And this brings me to our study site and the first finding of the LSD in the Eastern Alps in the glacial lacustrine unit of our sediment course from Lake Blancy. It is an inner alpine lake located in the western Austrian Alps and represents a distinct and underexplored setting for LSD identification. Its topographic position south of the Alpine front questions the previous assumption that the tephra didn't cross the Alpine front and generally questions our understanding of processes related to the distribution. Identifying tephra in minerogenic sediments is hard and needs a systematic approach. So in our workflow, we start with CT scanning, where we observe lower density layer. And magnetic susceptibility revealed a strong peak, which could indicate iron sulfide, but can also suggest the presence of tephra. XRF scans showed peaks in components linked to volcanic minerals, such as iron, strontium, titanium. And with high-resolution micro-XRF mapping, we confirmed this with iron peaks highlighting a distinct layer. Finally, the microprobe confirmed the volcanic nature, and we were able to correlate it with the Lachase eruption. We found several volcanic minerals, such as assemblages of sanidine crystals, olivine crystals, clinopyroxenes with nice sonations, and lots of altered glass alongside. And the alteration relates to the alkaline conditions in the lakes. And these volcanic minerals themselves stand out, especially in Blancy's dolomitic catchment, where they just do not belong. So with this workflow, we narrowed down the search from broad indications to pinpointing the tephra at a specific layer, which is essential in challenging glass-poor environments like in Blancy. And that's why I highlight the role of tephra minerals in cryptotephra research. Many studies focus on glass, but in environments where glass is altered or available in very small amounts, this can lead to missed layers. And for the LSD in particular, we know that there is a variety of minerals commonly found and linked to the eruption. And considering this gives the chance that cryptotephra layers are not overlooked. And ultimately, this age marker helps to refine our age depth models. Now I'm coming back to the fallout distribution. The classic three-lobed pattern is often explained by eruption height and wind. But now we have findings from the southwest, from the north, and we found high amounts in the Bohemian forest and now Blancy, showing the ash crossed the Alpine front. And this challenges the idea of strict eastern limits. So we suggest that political boundaries, research gaps, and site availability have shaped the map as much as actual fallout dynamics. And these new finds outside the established fallout zones highlight the potential in other regions like the Austrian Alps, the Czech Massif, Carpathians, Pannonian Basins, and the Southern Alps. So one goal is to integrate our scanning workflow into more sediment studies. It makes cryptotephra detection faster and strengthens age models, especially where radiocarbon dating is tricky. Another point is to expand mineral-based cryptotephra analysis, helping in environments where glass is poorly preserved and ensure that cryptotephra layers are not overlooked. The next goal is to target more unconventional settings like paleo lakes or alpine lakes, broadening the range of natural archives, and with that provide valuable new records for age dating and environmental reconstruction. And finally, we need to study beyond existing fallout zones. This helps refine ash distribution maps, but also improves the chronological framework for Europe and the late glacier. As mentioned in the beginning, we can only estimate the distribution, the impact of the eruption when we understand the fallout. And we need to advance our understanding to understand the impacts on climate, ecosystems, and human societies. All of this is essential for future volcanic risk assessment and understanding Earth system changes within a precise temporal framework. Thank you very much for your attention.